Sergeant, and this is lesson 9.4, the ideal gas law. Today we're going to talk about the ideal gas law along with Avogadro's principle and law. You will need a piece of notebook paper in addition to your packet for this set of notes. So Avogadro's principle says that equal volumes of gases at the same temperature and pressure contain equal number of particles. Those particles, the atoms, molecules, and formula units, we can compare them with the unit of a mole. So 1 mole of gas equals 22.4 liters. And we can use this as a conversion factor whenever gases are at standard temperature and pressure. So we can write this 1 mole over 22.4 liters, or 22.4 liters over 1 mole, depending on what we are trying to solve for. Our next problem says 0.0680 moles of oxygen gas are produced in a reaction and we want to determine the volume that it occupies at STP, standard temperature and pressure. So the only number and unit that we're given is the number of moles, and we want to find the volume. So we're going to use that conversion factor we just talked about to find the volume because it is at STP. So we need to take 0.0680 times 22.4, and you should find that you have 1.52 liters of oxygen gas. Our next problem says the main component of gas used for home heating and cooking is methane, CH4, and we want to calculate the volume that 2 kilograms of methane gas will occupy at standard temperature and pressure. So we need to convert from grams to moles in order to find the volume. So if you remember, 1 kilogram equals 1,000 grams. So 2 kilograms is going to equal 2,000 grams. So we are going to start with our 2,000 grams of methane, so CH4. And in order to convert from grams to moles, we need to find the molar mass of methane. So carbon's average atomic mass is 12.01, and we have 1 atom of carbon. Hydrogen is 1.01, and we have 4 atoms of hydrogen. So add these together and you should get a molar mass of 16.05 grams per mole. So we're going to put 16.05 grams on the bottom for CH4 and 1 mole on the top. So grams of CH4 cancel. We'd be left with moles, but we can just go ahead and use that conversion factor to go straight to liters instead of doing a separate calculation. Moles cancel, and we're going to be left with liters. So we need to take 2,000 times 22.4 and divide it by 16.05. And you should find that you have 2,791 liters of methane at standard temperature and pressure. Okay, so Avogadro's Law, that is where your extra sheet of paper that you got out is going to help you out. Avogadro's Law is not in your packet this year. So Just as a reminder, Avogadro's principle says equal volumes of gases at the same temperature and pressure contain equal number of particles. So the equation for Avogadro's law is the volume of the first gas divided by the number of moles equals volume of the second gas divided by the number of moles. So as volume increases, the number of moles or the amount is also increasing. And as one decreases, the other decreases as well. So this is a direct relationship. All right, so just kind of a visual for Avogadro's law. You have two bunnies. As the number of particles increase, they're happy. They make more bunnies and more bunnies and more bunnies. The volume, the space that it's going to take up, is going to increase, which is where we get V1 divided by N1 equals V2 divided by N2. So our first example problem says that two balloons are filled with different amounts of an ideal gas. One balloon is filled with 3 moles and it fills 30 liters. The other balloon encloses a volume of 45 liters and we want to determine the number of moles. So remember your equation, V1 divided by N1 equals V2 divided by N2. So V1 is going to be 30 liters. N1 is going to be 3 moles. V2 is going to be 45 liters. And we're going to look for N2. So from here, we need to cross multiply similarly to what we did to solve for Charles' law and Gay-Lussac's law. So you're going to have 30 liters times N2 equals 45 liters times 3 moles. To get N2 by itself, we need to divide by 30 liters on both sides. So N2 is going to equal 4.5 moles. Our next example says calculate the volume of 0.081 moles of oxygen at STP, and we want to find the volume. So there's a couple ways that you could actually work this problem. You can start off with the equation, so 0.881 moles. We're trying to find V1. But what do we set it up next to? Well, we can use the proportion of 22.4 liters divided by 1 mole and do some cross multiplication, which is going to be V1 is going to equal 0.881 moles times 22.4 liters. Or you could also set it up like this. We're only given the number of moles. And then use the train tracks with your conversion factor to solve for the liters. You're going to get the same answer, which should be 19.7 liters. Okay, so that is Avogadro's law. Go ahead and flip back to your packet to take a look at the ideal gas law. So up until this point, with Charles' law, Boyle's law, Lussac's law, the combined gas law, all of them have assumed that the amount of gas is constant. But the ideal gas law is going to help us determine how much gas there is. So the equation is PV equals nRT. Also, sometimes it's referred to as the Pivnert equation. So, pressure has to be in atmospheres or kilopascals. Before, we've been able to use pretty much any unit of pressure. With the ideal gas law, it has to be one of these two. Volume has to be in liters. So if it's in milliliters, you got to convert it to liters. The amount needs to be in moles. So if you're given grams, you need to convert to moles. And then temperature, just like all the rest of our gas laws, it has to be in Kelvin. So R is something that we haven't talked about, and R is the gas constant. The gas constant, which number we use, which is a mathematical relationship of all the variables, depends on what unit you have for pressure. So if you have kilopascals for your pressure, you're going to match it with the gas constant that has kilopascals in it. So it's 8.31 liters times kilopascals divided by moles times Kelvin. Where if you have atmospheres, your gas constant is going to be 0.0821 liters times atmospheres divided by moles times Kelvin. So your pressure unit has to match that in your gas constant. Okay, so this first example problem for the ideal gas law says how many moles of gas are contained in 890 milliliters at 21 degrees Celsius and 750 millimeters of mercury. Since there's more variables, just like I did with the ideal gas law, I kind of like to write them out. So that way I can take a look, determine, do I need to convert anything or am I good to go? So pressure is 750 millimeters of mercury. The volume is 890 milliliters. We want to determine the number of moles. And the temperature is 21 degrees Celsius. We'll come back to the gas constant in a little bit. So none of these variables have the correct units, so we need to do some conversions. So we have a conversion factor going from millimeters of mercury to atmospheres. So 1 atmosphere is equal to 760 millimeters of mercury, which 750 divided by 760 is going to give you 0.987 atmospheres. Volume is in milliliters. We need to convert that to liters by moving our decimal 3 places to the left. So 0.890 liters. And then our temperature is in Celsius. We need to convert it to Kelvin. So we're going to add 273, which is going to give us 294 Kelvin. So the other thing I like to do with the ideal gas law is rearrange my equation before I plug in all of these numbers. Just kind of helps me save a couple steps from what I need to write down. So we're looking for the number of moles. So we are going to divide by RT on both sides. And then, so my new equation is N equals PV divided by RT. So the only thing I have left to do is figure out what my gas constant is. My pressure unit is atmospheres. So we are going to use the 0.0821 liters times atmospheres divided by moles times Kelvin. So now I'm just going to plug things into my equation. Pressure is 0.987 atmospheres. The volume is 0.890 liters. the gas constant 0.0821 liters times atmospheres divided by moles times Kelvin. And then my temperature, 294 Kelvin. So atmospheres are going to cancel, liters cancel, and Kelvin cancels. So we're going to be left with moles. So N equals 0.987 times 0.890 divided by 0.0821 times 294. And you should get 0.0364 moles. Okay. So let's take a look at our next problem. It says if 2.8 moles of gas occupies a volume of 23.3 liters when the pressure is 124.6 kilopascals, we want to determine the temperature in degrees Celsius. So the pressure is 124.6 kilopascals. Volume, 23.3 liters. Number of moles is 2.8. We don't know what our temperature is. That's what we're solving for. So since my pressure is in kilopascals, my gas constant is going to be the 8.31 liters times kilopascals divided by moles times Kelvin. And then with my gas law equation, I'm going to go ahead and solve for T before I plug things in. So T equals PV divided by N times R. So my pressure is 124.6 kilopascals. The volume is 23.3 liters. Number of moles is 2.8. And then the gas constant, which is 8.31 liters times kilopascals. Moles times Kelvin. So kilopascals cancel, liters cancels, and moles cancel. We're going to be left with Kelvin. So the temperature is going to be equal to 124.6 times 23.3 divided by, in parentheses, 2.8 times 8.31. So your temperature is going to be equal to 124.77 Kelvin. But we want it in degrees Celsius, so we need to subtract 273. And you should get negative 148 degrees Celsius for your Celsius temperature. Okay. And then we have one more example problem. It says if a sample of neon gas occupies 2.50 liters and a temperature of 355 Kelvin at a pressure of 1.43 atmospheres, we want to determine how many grams of neon are present. So our pressure is 1.43 atmospheres. Volume, 2.50 liters. Number of moles, we don't know. And the temperature is 355 Kelvin. So we're going to first solve this problem for the number of moles, and then go from moles and use the molar mass to find the grams. So our gas constant that we're going to use is the 0.0821 liters times atmospheres divided by moles times Kelvin. So, take the equation and solve it again for the N. So N equals PV divided by RT. So pressure is 1.43 atmospheres. The volume is 2.50 liters. And the gas constant, 0.0821 liters times atmospheres divided by moles times Kelvin. And then the temperature is 355 Kelvin. So atmospheres cancel, liters cancel, and Kelvin cancels. So the number of moles is going to equal 0.123 moles. So now we need to go from moles to grams. So we need the molar mass of neon. And neon is a noble gas, so it's not diatomic or anything like that. So it's the same as the average atomic mass. So 1 mole of neon equals 20.18 grams of neon. Moles cancel. 0.123 times 20.18 should give us 2.48 grams of neon. Okay, so that is the ideal gas law. Here are the last two homework assignments. This one was given in class the day of a lab, and so these are over the combined gas law, page 450, numbers 11 through 13. And then the Avogadro's Principle law and the ideal gas law is page 453, numbers 20 through 22, 25, and then page 455, numbers 26 through 29. If you have any questions, feel free to stop by and ask me. Thanks for stopping by. Have a great day.